Okay, today I'm going to explain you the first part of the activity 5. So, first, I would like to explain the usefulness of computer simulators to represent a physical system. The use of a computer to represent the dynamic responses of one system by the behavior of another system modeled after it. A simulation uses a mathematical description or model of a real system in the form of a computer program. This model is composed of equations that duplicate the functional relationships within the real system. When the program is run, the resulting mathematical dynamics form an analog of the behavior of the real system, with the results presented in the form of data. So that is a usefulness. Now I'm going to indicate you the methodology to design a physical system using a computer simulator. Here you can see a map where you can follow the steps that are there, and each step is going to take you to another. So depending of the step that you take is the result that you are going to have. Like if we follow real system and then we go to perform experiments and then we go to experimental results, it would be compare and improve model, or also can be compare and improve theory. So depending on what you follow is what you're going to have as a result. And now I'm going to explain you the requirements and information that you need to design a physical system using a computer simulator. You here can see a picture where it has step by step the requirements that you need. So first is physical system, then you need to identify the modeling domain. It could be physical, chemical, biological, etc. Then you identify the law, the hypotheses governing in the system domain, physical, chemical, biological, laws or hypotheses. It depends. Then you formulate the mathematical model with initial and boundary conditions. Then you solve the mathematical model, interpret the results, and propose the changes required in the systems to achieve desired behavior. And finally, you finish in your physical system.
That you must follow to design a physical system, specifically for a skating ramp that has form of a parabola. First, you have to make the graph. Then choose the skater. Eliminate the friction and put the speed at the half. You let the skater fall from a height of 10 meters. Then you find the potential and kinetic energy. And finally, calculate the velocity. This is it of my part. Thank you, Tony.
For the part A, here we have on the program a parabola-shaped ramp with a loop in the middle of it. The highest place in the loop is in the 6th meter and the highest part of the ramp is on the 10th meter. When the skater is put into the ramp, travels the entire ramp and returns to its point of origin. Also we count with the skater, which mass is 75 kilograms.
So here the potential energy it's the biggest when the skater is at the tallest point of the ramp because the potential energy consists on the mass and the height. So as we can see in the ramp the highest point is 10, so that's why he got the most potential energy there. And for the kinetic energy, when he is when he reached the zero meters, nearly to enter the loop of the ramp, he gets the most kinetic energy. This is because the kinetic energy depends on the velocity. So that's the point when he get like more velocity on all the ramp. And also when he's at the top of the loop at the 6 meter, he gets half of the kinetic energy because he gets velocity but not enough to full the kinetic energy. We can get the velocity of the skater by using the formula and substituting our values. So this will give to us 8.8 meters per second.
Hello everybody, we're going to make the part 3 of the activity 5 of the Matter and Energy course. First of all, we have to calculate the minimum initial height that allows the skater to complete the loop, and to make this, first we have to determine which is the minimal velocity that the skater needs to pass the top of the loop. How we're going to make this? Well, it is easy. We have the Newton's second law and a equation that is based in it. The Newton's second law is force equal to mass times acceleration. That, as we know, is the Newton's second law. So the following equation that we are going to use is the following. Centripetal force is equal to mass times gravity. Why? We have the centripetal force because it is a loop. What is a loop? It is like a circle, but like it is like a ramp. Now we know it. So the centripetal force is the force in the Newton's second law. Mass is mass and gravity is acceleration. So in this equation we have mass in both sides. So we can eliminate. As we can see, it is eliminate. So we have to pass to clear the velocity. Now, velocity square is equal to gravity times radius. Why? Because radius is in a division and we... Now, velocity square is equal to gravity times radius. Why? Because radius is in a division and we have to pass it into a multiplication. Now, it is square the velocity, and to pass it to have the only variable, we have to pass it to a square root. So velocity is equal to square root gravity times radius. With these equations, we can have the minimum initial velocity that the skater needs to have to pass the loop. So we have that velocity is equal to square root of 9.8 meters over second square, that is the gravity, times the radius, that is 3 meters. Why 3 meters? Because the loop is 6 meters as the problem said. And why? Because the height is like a diameter, so the radius is a half, so it's 3 meters. So we solve it. 9.8 times 3 is 29.4 meters square times second square and the root square of that. So velocity is equal to 5.4221 meters over seconds. Now this is the minimum initial velocity that the minimum velocity that the skater will have in the top of the loop. Now that we have this equation, we can calculate the minimum initial height that the skater will need to pass through the loop. Now, we have the principle of conservation of energy, that is U plus K equal to U plus K initial and final. So, U is potential energy, K is kinetic energy. In the first part, we have that initial energy is potential energy plus kinetic energy. The potential energy, it exists as we can see here, and the kinetic energy doesn't. Why? Because it is not in movement, it doesn't have motion. So it is equal to potential energy plus kinetic energy in the final part. Now we have the potential energy and the kinetic energy both in this part, because it is like in the part of the top of the loop, because we have the velocity in that instant, so we have both. Now we have that the potential energy is my mass times gravity times height, and we have it in the both sides. So mass times gravity times height is equal to mass times gravity times height. So that is the potential energy, and in this part we have two kinetic energy. So m times g times h plus 1/2 of mass times velocity squared. Now with this equation we have to get this value of the h, that is the height, the initial height, and we have to substitute all the other values. So the mass is equal to 60 kilograms because the problem said at the part 1. Then we have the gravity, that is 9.8 mass meters over second square, because it is a constant, times height, that is the variable that we want to know. It is equal to 60 kilograms times 9.8 meters over second square times 6 meters, that is the height that the loop have, and is a part of the top of the loop. So it is like determinant of the part that we are calculating. So plus 1 meter, 1/2 of 60 kilograms, that is the mass, times the velocity that we have here, that is 5.4221 meters over second square, and we have the following, that is 588 newtons, that is the 588 newtons, that is the product of this, times height, that is the variable that we have to know, equal to 3528 joules, that is the product of this equation, and that plus 881.9750 joules, that is the product of this equation. Now we have that 588 newtons times height is equal to 4,409.9750 joules, that is the product of this addition, is the answer of that addition, and we have to pass that 588 newtons in a division, because it is in a multiplication in this side. So we have that height is equal to 4,409.9750 joules over 588 newtons. So now we have the h. The h is the initial height, because it's in this part of the equation. The initial height is going to be 7.4999 meters. So now after all this equation, we have that the minimum initial height needed by the skater is 7.5, is in this part of the equation. The initial height is going to be 7.4999 meters. So now after all this equation, we have that the minimum initial height needed by the skater is 7.5 meters approximately, and that is because it's a frictionless event. And now we have that with this height it will pass the loop with this velocity. Thank you for your attention.